Yeah, very good morning to one and all present here. And today we are going to see about the topic is a column. Let us know what is in a column first in this unit of this thing. What is a column here? That, Oh, what is a column? A column is defined as a vertical load-bearing member supporting an axially compressive load chiefly. So this is a main a function. We may call it as a function, or we may call it as a definition of a column. This member is transmitted the load to the structure to the foundation. This is the main role of the column here. The reinforced concrete building beams, floors, columns are cast monolithically and built monolithically. Already I've seen this, and this is a small intro about the column. And let us have some pictures here about the column in the field and it's connecting with the beams on the column and below the footing, above the footing. And this is some of the cross section of the column. Let us see some of the cross sections of this column. So here we may see this is the reinforcement detailing, and this is an syrups detailing of the column. We may have that this is a tie, and this is a longitudinal steel, and this is a traverse steel, and difference is a pitch. So for circular pitch, we have a pitch and the spiral here. Okay, so this is the cross section of a column. So let us see about the some cross section. The traverse steel is nothing but of a ties. We call it as the syrups in the beam, and we call it here as a traversing steel or a ties. And in the spiral, we call it as where the circular column, we have two kind of reinforcement. One is traverse steel like a ties and like a spiral. In the spiral, the different distance between this each and every spiral, we call it as a pitch. And this was the difference. Right. So longitudinal reinforcement and traversing reinforcement. Here we may see which is a longitudinal reinforcement is the main bars and traversing is a ties. So longitudinal reinforcement to assist the concrete and resist the compressive is due to the overall size of the column to resist any tension and might develop the bending caused by the traversing load of eccentric load of a moment to reduce the effect of creep shrinkage due to the steadiness of loading to prevent delay in certain brittle of collapse. So this is some of the functions which is going to be dealt with in a longitudinal reinforcement and it imparts the necessary ductility to the material of column. Yeah, that's very important to prevent buckling of longitudinal bars. This is for the traversing to prevent longitudinal splitting of concrete. So when the splitting of concrete can be avoided and the resisting the diagonal resistance of the tension of the traversing should and conforming in the concrete and to prevent the delay in sudden collapse. So these are all some of the functions and the uses of the longitudinal reinforcement. Why we go with some longitudinal reinforcement and traversing reinforcement is here. So right, so this is some of the effective length we used in columns. This is pinned support and fixed support, pinned at both ends. Effective length is L, and effective length, that is, effective length is the column which is defined as the distance between the successive inflection points to point the moment is zero. So you may call it as an utilization length or a successful points that has a zero of moment start from, that's called as an effective length. So both at pinned L is equal to L and one end is fixed and both and fixed at both end which is 0.5 L which is effective length and which is one end is fixed and another end is pinned which is 0.7 L and one end is fixed and another end is free which is 2L. This is some of the effective length and we have this in the code also of IS456 and table 27 I hope. The effective length, the recommended value as, yeah, as it is. You can see the page number 98, table number 28, yeah, which has a different condition of IS456. Slenderness ratio. The slenderness ratio is very, very important in all type of column to identify what type of a column, which is a short column or a long column, or how long we are going to define or design this column. We are going to see slenderness ratio is equal to effective length by least lateral dimension. So lateral dimension is L into B, and that the least lateral dimension of the column can be taken. The simplest engineering definition we may call it as L effective by R, which is radius of gyration. And this is a small thing and slenderness ratio is L effective by R. Radius of direction is root of I by A, that is in moment of inertia by area, right? So column that depends on the ratio. You may see here we have a three type of column. This is not a column, actually pedestal compressive. Okay, let us see the very simple manner of differentiating a long column and short. We have two column, this is long column and short column. When the effective length by the lateral dimension is less than 12 is short column, is above 12 is long column. Short column is fails in crushing and long column fails by buckling. Slenderness ratio, it should be less than 45 and greater than 45 in long column, subjected to compression strength, subjected to buckling stress. Radius of gyration is more and radius of gyration is less. Load carrying capacity is more and load carrying capacity is less in long column. So you prefer always a long column, not a long column by a short column. Okay, maximum in the field. So this is a condition of loading we have in the column. One is axially loaded, uniaxially loaded, and biaxially loaded. You see in the axially loaded, which will be loaded and be centrally acting in the centroid, and load will be acting at the distance of some distance of Ex is nothing but of uniaxial in the direction of both Ex and Ey. That is both direction. That is the biaxial. So he let me know we have only the axial load here, axial load with a moment at a direction, and axial load with a moment at two direction, which is nothing but of a biaxial column. So let me have some picture here to identify the axially loaded or biaxially loaded column. So when we see that the red rounded is totally an axially loaded column, and which has the blue is uniaxial loader. That is one end will be having moment, and the another A3, D3, and A1, D1 is all uniaxially, biaxially loaded, such as both direction of the load. So these are the some of the ISO requirement for the longitudinal reinforcement bar, which should have the percentage of 0.626% of gross sectional area, is as per IS 456 2000, class 26.5.3.1. So minimum bar is 4 for a square column and 6 for a circular column. For the traverse reinforcement, the pitch of least lateral dimension of the column are 16 times of the D or 3 mm. The diameter should follow 0.25 times of diameter. So these are all some of the reinforcement should be allowed that were given in IS 456. So these are some design assumptions which is in IS 456. The eccentricity formula E minimum L by 500 plus D by 20. So minimum of 20 mm can be allowed for the eccentricity. So this is some of the design procedure for mm, under axial condition of column. So first we have to identify the effective length, which is in page number 28. Less slenderness ratio already we know can identify the short column or long column, and minimum eccentricity also can be identified. And based on which the class 71 page number, you can put the PU zero point 0.4 FCK plus DSC 0.67 FESCY, based on which you can identify the reinforcement detail. So this is 1.5% maybe extra when it is column is in circular section. And this is some of the spacing which has been given in the codal for a column, and that can be referred. And thank you for watching this, and thank you for watching this video. Thank you.